Good evening. Today we are going to be talking about harmonic oscillator. It is a very important kind of potential with a wide range of applications. And we are going to solve, well, kind of, the Schrödinger equation for the harmonic oscillator. And we will find that there are certain energy eigenstates, just like the infinite potential well, but the kind of energy levels that we are going to see will be different because the potential is different. So as you know, the harmonic oscillator potential is of the form 1/2 kappa x squared, where x is displacement from the equilibrium of the oscillator. And we'll discover that the energy levels are labeled by a number n, which can be 0, 1, 2, 3, etc. And the energies are given by n plus a half h bar omega. And omega is related to this kappa, which appears here, and the mass of the particle, which happens to be in this potential, via this relation, square root of kappa over m. This is this is exactly what you get also in the classical case, that the frequency of the oscillator is given by square root kappa over m. So it carries over here, but the energies will be quantized. We are going to see that a function like this, a e to the negative alpha x squared, will solve the Schrödinger equation, and it is going to be the ground state of the harmonic oscillator. Okay, so here is the Schrödinger equation. And this applies to, as I said, many different cases. For instance, a diatomic molecule is represented, of course, by two atoms, all right? And as we will see, the potential between the two atoms can be approximated as a harmonic oscillator potential. So the atoms are going to vibrate as if they were held together by a spring. This is very general. We'll see that. Another application is sound waves in solid, for instance. Vibrations in materials are also described by harmonic oscillators. Okay, first, let's take a look at the ground state of the harmonic oscillator. So here is the equation, and we are going to see if this function satisfies this equation, and if it does, what kind of E will we get? Okay, so notice that Schrödinger equation, or time independent Schrödinger equation, has two unknowns. One is the function here, psi of x, the probability amplitude, and the other one is E. Okay, this is called very generally a eigenvalue problem, where you find the eigenvalue, which is E, as well as the eigenfunction, which is psi of x. Okay, so let's try to go to the next step. So what we want to do now is, in order to plug this into this equation, we need the second derivative. So you differentiate it once and you differentiate it again, and we get this quantity here. So I'm going to substitute this in here, all right? And this one over here and here, okay? So I end up with this. So this is the second derivative. Here is the a e to the negative alpha x squared right here. And on the right-hand side, I get the same thing. Notice that the a's cancel, and e to the negative alpha x squared also cancel. So the only thing that we are left with is this equation. Now this equation has to be satisfied for arbitrary x, which means that this coefficient must be equal to 0 and this constant also must be equal to 0. When you set this equal to 0, you get alpha equal to square root of kappa m over 4 h bar squared. All right, just solve this equation. And then also E is equal to h squared alpha over m, and you substitute alpha in here and you get this. And notice that square root of kappa over m is omega. So you get E equals 1/2 h bar omega. It turns out that this is the lowest energy that a harmonic oscillator can have. Let me see if you can answer this question a little bit. I'm going to discuss it after I pause a little bit for you to kind of think about it. So what we have here, given that the energy of the ground state, that's the 0, is 1/2 h bar omega, and given that omega is given by square root of kappa over m, we want to answer this situation. Two molecules have different values of kappa, as shown. So these are the potentials, 1/2 kappa x squared for two different kappas. In classical mechanics, which molecule has the lowest ground state energy? Lowest ground state energy for classical mechanics. Okay, well, we don't call it ground state in classical mechanics. We just say the lowest energy. And obviously you can see that the lowest energy that any particle can have is this. So basically imagine that this is like a, I don't know, a bowl, and you put a ball in here. It's going to oscillate back and forth here. And at the end, it's going to just end up here. This is the ground state. And it doesn't matter whether you have this kind of a bowl or this kind of a bowl. The particle eventually ends up here. So that's for the classical case. What about quantum case? Which molecule has the lowest ground state energy? The ground state energy is 1/2 h bar omega. And omega is given by this quantity here. So given these, you should be able to answer which particle has the lowest ground state energy. So they have the same mass. All right. Here is the ground state. You have 1/2 h bar omega for any harmonic oscillator. H bar, of course, is the same for both of them. It's the same for anything. It's just a constant, universal constant. So you have to look at omega. Which one of the particles has the lower omega? And omega is square root of kappa over m. So which one of these two do you think has a lower kappa? Well, the potential is 1/2 kappa x squared. So the larger the kappa is, the narrower the potential. In other words, as a function of x, the potential goes to larger values okay, for lower X. So this has a smaller kappa, this has a larger kappa, which means that this is going to have a lower potential energy. So blue is the right answer. Okay, so this is what we will discover if we could solve the Schrödinger equation completely, not guess, but actually solve them. And if you do, you'll get for E, n plus 1/2 h bar omega, where n could be 0, 1, 2, 3, etc. Now for n equals 0, we get 1/2 h bar omega, which is the ground state. And for n equals 1, we get 3/2, n equals 2, 5/2, etc. And notice that all the energy states are equally spaced, okay? The difference between the energy levels is always h bar omega, okay? This is in contrast to infinite potential well, if you recall. The energy went as n squared, where n equals 1 was the ground state. So these are the energy levels for a harmonic oscillator. As I said, solution to it is kind of sophisticated, and you have to have some background in differential equations and partial differential equations. We are not going to actually go through that. We just borrow the result, namely that E is n plus 1/2 h bar omega. And we just discovered that the ground state is of the form a e to the negative alpha x squared. All right, this is one of your checkpoints. So it is similar to what we have been talking about. So we have in cold atom experiments, we use laser to trap atoms in a harmonic well. And then low frequency light can be used to excite the atom within the well. The trap can have either lithium or rubidium atoms. Lithium atoms are lighter than rubidium atoms. The experimenter keeps the potential applied by the laser constant, which basically means that kappa is constant, and measures the absorption frequency for both lithium and rubidium. Suppose that FLI is the first absorption line when lithium is in the trap, and FRU is the first absorption line when rubidium is in the trap. And we want to see which one of these is true. And all you have to do is just look at h bar omega, where omega is equal to square root kappa over m, all right? So omega goes inversely, kind of. So omega increases with decreasing m, okay? So the lighter is going to have a higher energy, and therefore it requires higher frequency to excite it. So this is the right answer. Lithium is lighter, therefore it has higher energy, higher frequency, and therefore higher energy. As you probably recall from our discussion of infinite potential well whenever you have discrete energy eigenstates. When a particle makes a transition from a higher level to a lower level, it emits a photon, and in order to go from a lower to a higher, it should absorb a photon of definite frequency, okay? So this one went from 7/2 h bar omega to 5/2 h bar omega. Therefore, the energy of the photon emitted was h bar omega, the difference between these two. And if you go from 7/2 h bar omega to 3/2 h bar omega, then the energy is going to be 2 h bar omega. That's the energy of the photon. Now, as we said, different potentials yield different energy levels. This is the kind of energy levels that you get for harmonic oscillator. Now, if you had the Coulomb potential, remember that Coulomb potential is like 1/r, so it varies as the distance between the particles. And it's positive or negative depending on the sign of the particles. But Coulomb potential has its own energy levels. And one of the first successes of quantum physics, which was actually performed, the calculation was performed by Schrödinger in January of 1926, and it gave the energy levels of the hydrogen atom. Okay, so the first thing that Schrödinger did when he discovered his equation was to apply it to hydrogen atom, which is the simplest kind of atom with a Coulomb potential, and he could solve the equation. Namely, he could find both the psi function as well as the energy eigenvalues, and he found the formula for the energy eigenvalues, which agreed with what Bohr discovered about 13 years earlier. Okay, so that was the beginning of the quantum theory, and people started to believe in that. So, and then, people applied it to various other elements, not just hydrogen, and they discovered that different atoms have different spectral lines. So let's see the spectral lines of a few elements.
This is a diffraction grating. We have talked about it before when we were talking about waves. One of the useful properties, or what the diffraction grating is used for, is to look at the spectral lines of the elements. Okay, as you can see here, we have 4 elements: hydrogen, neon, helium, and xenon. And you can take a look at the light as it goes through the diffraction grating. And as you will see, instead of a continuous light, spectrum of light like the rainbow, you are going to see spectral lines. Okay, so first let's take a look at what you will see when you have just an ordinary light bulb. Okay, I'm going to turn the lights off so you can see. We are going to hold this in front of the camera, and then you will see what a continuous spectrum is and what the spectral lines of various elements are. Okay, so let me turn the lights off. And I'm going to first start with just ordinary light. When you look at the light through the diffraction grating, you see a rainbow. And I hope everybody can see the rainbow, okay? However, if you look at the light coming from various elements, atoms, then things are going to look differently. So let's see what this gives you. This is neon. Okay, so if you look at neon, you see it has a lot of spectral lines, vertical lines of various colors. I'm going to switch to another element, which is hydrogen. And now you should be able to see 4 lines. Hydrogen emits 4 visible lines. Of course, it emits other electromagnetic waves, but they are not visible. And one of the successes of the quantum theory was to predict what kind of spectral lines you would see for hydrogen. Okay, you should see 4 of them. And of course, you can change elements. Here is helium. You see the spectral lines of helium. And maybe I can get to xenon. And here is the xenon. Okay, now okay, I'm going to turn the lights on and just mention that spectral lines of various elements are like fingerprints of those elements. And each one has its own particular spectral lines. And this is what astronomers and cosmologists use to determine what kind of elements exist on, let's say, planets, stars, galaxies, and why they emit the kind of light that they do.
Okay, as I said, different spectra correspond to different potentials, all right? Over here, which one might be described by an infinite square well? If you remember from our discussion of infinite square well, we saw that the energy would go as n squared times the ground state energy. So if this is the first excited state, so that's n equals 2, then the next one is going to be 9. So this is 4, this is 9. So if we were to choose between these two for the square, well, then it would be B. Okay. Now, this is kind of a silly equation because if this is 4, then to get 9, I have to go 5 units up here, which is about here, right? So neither is also possible. In order to make it actually exactly the infinite potential, well, I should bring this down here to about here, because from here, if this is the ground state, from here to here is 4, and from here to the second excited state is 9. So the difference between this and the next one should be 5. If this is 4, then 5 is very close to it. Obviously, this is wrong. Anyway, you know what I'm trying to get at. Now, if we know which molecules are present, okay, we can determine the kind of energy levels associated with them, because molecules are typically like harmonic oscillators. So if I know what kind of molecules I have, namely the mass M and the harmonic oscillator associated with it, then I can determine what this is, and therefore what kind of photon is emitted if the oscillator goes from one energy level to the next one down. Okay, so this would be the energy of the photon, and this is the energy difference between the two levels. So if I know kappa M, then I can determine this lambda, okay? So it turns out that infrared and microwave are the dominant emission and absorption spectra of many common molecules, okay? Now, infrared has some really interesting properties, which I can demonstrate to you. By looking at objects that block, for instance, infrared, and objects that could be transparent to infrared, but they block visible light. So let's take a look at
that. This is an infrared camera. I'm going to light this candle, and notice that it can see the flame, all right? Okay, you can clearly see the flame up there. And of course, you can see the flame through the camera, okay, through the optical camera. And so if you were in the class here, you would see a flame. But let's see what happens if I put a glass beaker on top of it, all right? The camera can still see the flame, but the infrared camera can't. So you can see that the flame is gone. And the reason is that infrared cannot go through the glass.
Okay. And it is trapped inside the glass. So you, everybody, if I focus it, okay, so now, hopefully you can see me. And that's because human body emits infrared light, okay? And you can see now my face But as soon as I put my reading glasses, these are not sunglasses, these are just reading glasses on, you see that the infrared, it looks black because nothing, no infrared light is coming out of my glasses towards the infrared camera, so it lost the infrared. So if you're sitting inside a car, you are emitting infrared, and if it is winter, the windows are closed, and the infrared is trapped inside. That is called the greenhouse effect. Okay. Also, notice another thing. Again, okay. I have here, alright, I can ask you, for instance, how many fingers do I have, here, and you can't really see it, alright, but if I go to the infrared camera, you can see I have 2 fingers up, right? Right, so the reason is that light cannot go through this dark plastic, but as you can see, my hand is visible to the infrared camera. So infrared goes through the plastic, but not through the glass.
Okay, infrared and microwaves, as I said, are the kind of light that is emitted or absorbed by molecules. Okay, now here what you have, let me explain what this is. This is called solar radiation spectrum. All right, the sunlight comes in, and it's in the form of a black body radiation, which is of this form here. We are not going to talk about that, but those of you who will be in 213 will see that. So it is a kind of intensity, okay, as a function of wavelength. So the sunlight is very weak at very low wavelengths or short wavelength, is maximum at about 500 or so nanometers. That's about green. And it falls down, okay, to 0 at infinity. Okay, so the intensity, let's say here 1500 nanometer, which is infrared, is very low. Now, that is not what I'm trying to get at. What I'm trying to get at is that the sunlight comes in, and here is the sunlight coming in. But then, because of the atmosphere, because of the presence of some molecules in the atmosphere, part of the sunlight is going to be absorbed. So if you look at the sunlight, for instance, as it passes through the atmosphere, for instance, in this case, it is almost 0. There is nothing here. Why is that? Because the water vapor, which is in the atmosphere, absorbs most of the frequencies that are in this range. So 1250 to 1500, for instance, nanometer, that's infrared. So is this. Infrared has a range of about 780 nanometers to 1 millimeter. So everything from here on, all the way to here is infrared. And you can see that hydrogen absorbs many different kinds of infrareds because of the way that the transition between levels occur for hydrogen. Hydrogen is not a 2-atom molecule, but 3-atom molecule. So that means that it is a little complicated, and it has different energy levels at different ways. So that means that there are various places where H2O absorbs the sunlight, in the infrared in the sunlight. So here is about less than 1,000. Here is about I don't know, 1,100 nanometer. Here is a very strong absorption, which is about, I don't know, 1,300, 1,400, and so on. And then you also see CO2. CO2 is also a very absorbent of the infrared light. Okay, now the H2O and CO2, as you know, are what we call greenhouse gases. So what they do is they absorb the infrared and the microwave, all right, and then re-emit it. As they re-emit it, the infrared can't go, especially microwave, can't go back out of the atmosphere. Just like the glass that you saw in the demonstration. The glass, is opaque to infrared. Infrared cannot be transmitted through the glass. So similarly with the atmosphere. So that means that the energy that comes in the form of visible light through the atmosphere, okay, gets absorbed by the greenhouse gases and then re-emitted. But when it's re-emitted, it can't go out. So it's trapped inside, and therefore, we have this so-called greenhouse effect, which means that the temperature keeps rising. It is exactly the same as, the car. Okay, so visible light comes into the car, but the car, everything that is inside the car emits infrared. Okay, the chairs, the steering wheel, all of these emit infrared and microwave, but they can't get out of the glass. So the energy builds up inside, and that's how you get a hot temperature inside the car, especially in the summer. Okay, so here is another question for you. Two molecules have different values of kappa, all right? For each, an electron starts in the state with n equals 1 and transition to n equals 0. Which one emits the photon with the shortest wavelength? Okay, it doesn't say so. But we are assuming that the mass, okay, no, sorry, the mass of the, of course, electron has the same mass in the two potentials. So the mass is the same. All right, so this is the same. And the shorter wavelength corresponds to the higher frequency. Higher frequency corresponds to higher kappa. Higher kappa corresponds to a sharper rise in the 1/2 kappa k squared. So this one has with the shorter wavelength. So this orange one has shorter wavelength. Okay, so this is the summary of what we have been talking about. Schrödinger equation is given by this. U of x is the harmonic oscillator potential, which is kind of the potential of a spring. And the energy levels are given by this. N, remember, could be 0, unlike the case of the infinite potential well, where N started with 1. So here N could be 0 because you don't get 0 here. And omega is given by kappa, square root kappa over M. And this is the ground state energy of the harmonic oscillator potential. Okay, have a good day.